Hello everyone, welcome back to my YouTube channel. As you all know, myself is Kavya, currently pursuing my second year BE in Sri Venkateshwar College of Engineering, Bengaluru in the Department of Electronics and Communication. And here my USN is 1VE23EC043 and subject is Digital System Design using VERILOG. Subject code is BEC302 and here I am going to explain about the topic of designing of Mod 12 synchronous counter. First, let will know about the introduction part. That is, what is synchronous counter? A synchronous counter is the counter in which the clock input with all the flip-flops uses the same source and produces the output at the same time. Also, it is digital counter that uses a clock pulse to control the counting sequence and trigger all flip-flops simultaneously. This design eliminates propagation delays, making synchronous counters faster and more efficient than asynchronous counters. In the picture, we can see the circuit of asynchronous counter. This is using JK flip-flop, and next is Mod 12 synchronous counter. The synchronous Mod 12 counter is a digital circuit that counts through a predefined sequence of states in a cyclic manner following the Module 12 sequence, that is 0000 to 1011. Synchronous counters are designed in such a way that the clock pulses are applied to the CP inputs of all the flip-flops. The common pulse triggers all the flip-flops simultaneously rather than one at a time in succession. 4 JK flip-flops are required to make a Module 12 counter. Module 12 counter will count from 0 to 1. To represent 1, 1 in binary 4 bits are required 1011. Hence, 4 flip-flops are required as each flip-flop can have a state 0 or 1 at the output. Next is steps to follow for the design of synchronous counter. First step is determine the number of flip-flops required. Firstly, analyze the problem description and determine the number of flip-flops required to implement the synchronous counter. If n is the required number of flip-flops, then the smallest value of n is such that the number of states n, capital N, is less than or equal to 2n. Second step is draw the state diagram. Secondly, draw the state diagram that shows all the possible states. The state diagram is basically a graphical way of representing the sequence of states through which the counter progresses. In the state diagram, we can also include the case in which the counter goes to a particular state from invalid states on the next clock pulse. And third step is selection of flip-flops and excitation table. Select a particular type of flip-flop to be used to implement the counter and draw the excitation table. The excitation table is one that gives the information about the present states, next states, and required excitations of the flip-flop. Step 4 is obtain the minimized expression for excitations. Obtain the minimal expression for the excitations of the flip-flops by using any minimization technique such as K-maps. Fifth is draw the logic diagram. Finally, logic circuit diagram according to the minimal expression obtained in the step 4. In this way, we can design a synchronous counter. Synchronous counter may suffer from the problem of lockout, which means they may not be self-starting. A self-starting counter is a type of synchronous counter that will enter to its proper sequence of states regardless of its initial state. we can make a counter self-starting by designing it so that it enters to a particular state whenever it goes to an invalid state. Next is to design a module 12 synchronous counter, we should know about excitation table of JK flip-flop. Here I had given the excitation table of JK flip-flop for Qn and Qn plus 1 and JK are inputs. For 0 0 0 and cross 0 star and 0 1 1 and cross 1 0 cross and 1 and 1 1 cross and 0. And next is here I had given the logical diagram of module 12 synchronous counter. Here for all the 4 flip-flops, JK flip-flops, I had connected the clock for all JK flip-flops. Common is clock, and for all inputs and outputs I had given the terminals. And next is for JD, KD, JC, KC, JB and KA, I had designed the gates separately. And here is excitation table for QD, QC, QB, QA are the present states, and QD star, QC star, QB star and QA star are the next states, and JD, KD, JC, KC, JB, KB and JA, KA are the inputs. For JD, KD, we are taking the values of QD and QD star. For JC, KC, we are taking the values of QC and QC star. For JB, KB, we are taking the values of QB and QB star, and for JA, KA, we are taking the values of QA and QA star. Yeah, as referring the values of these, we will get the inputs of this present state and next state. And next is applications of mod 12 synchronous counter. First is digital clocks. Our counter, a mod 12 counter, can represent hours in a 12-hour clock format, that is 1 to 12 hours. It works in conjunction with mod 60 counters, that is for minutes and seconds. Second is frequency division, used to divide the input frequency by 12 in frequency synthesizers or clocks, useful in generating timing signals for other circuits. And third one is control systems, used in sequential control systems where 12 steps or states need to be tracked, such as traffic light control with 12 phases or cyclic manufacturing processes. And third one is decimal counters, works in digital systems requiring decimal to binary or binary to decimal conversion for applications limited to 12 values. And fourth one is event counting, applied in systems where events are grouped in sets of 12, such as rotational monitoring or repetitive process in industrial automation. And last one is calendar systems. In systems tracking months, a mod 12 counter is often used to cycle through the 12 months of the year. Thank you guys for watching my video. Please like and subscribe. Thank you so much.